Thank you, Vincenzo. It's very kind. Welcome everybody, and hope that you're going to find this presentation of use, and we'll find out a bit more about the area of printed electronics and what it can potentially do for you and your electronics developments that you've got in mind. The term is printed electronics in this presentation. Printable electronics is also used as a common term for this. We've never quite worked out what the difference is. So we tend to use them interchangeably. So if I use the word printable rather than printed, don't worry, it's all exactly the same thing. So the objective of this hour and a bit presentation is to try to give an idea of what printed electronics is. And that isn't an obvious question to answer. It's because it's evolving and has changed quite a bit over time. We'll go through a number of different areas, but what I'd like you to get from this hour session is an understanding of the techniques and components that we use in flexible circuits, understand the characteristics of the technologies that we use in flexible assemblies, and give you some sort of real life case study of a device that we've worked on for quite some time, in various forms at CPI, and hopefully that will give you a feel for how real printable electronics is. Specifically, the topics we're going to cover over the next 70 odd minutes is really looking at the characteristics, first of all, of printable electronics. We'll look at the different form factors that printable electronics can be used for, understand the components that are used in these systems, and look at the assembly techniques that we use to put them all together. There's quite a move to look to high volume manufacture of printable electronics, and so in the section on automation for manufacture, we'll look at some roll-to-roll production equipment that's being used to do assembly of these devices, and we'll also try to understand the range of applications that printable electronics is being perceived and used for currently and in the future. And we'll finish with a case study of a smart label. So I'll be happy to take questions at the end. If you've got any burning questions, do feel free to ask as we're going along, because it can make the flow a bit more interesting. So that will be fine as well. So what are the characteristics of printed electronics? Well, what is it? Essentially, it's an electronic system that's created using printing techniques. That kind of almost says exactly what it does on the tin, sort of thing, doesn't it? But what is meant by printing technologies? Well, there are a wide range of printing technologies that are used, and essentially most of these come down to the idea of an additive process. So we're creating circuits, both components, devices, and also the substrates that the circuits are going to go on to. We're doing that by using an additive process. So instead of the conventional printed circuit board where we start with a sheet of copper and remove the bits we don't want, subtractive process, we're going to use an additive process where we only put down the conductors and the materials, the sensor materials and the active semiconductors and the like. We only put those down where they're needed. So it's an effective and efficient way of doing circuit assembly. It can be very quick, it can be very versatile, it can be completely digital. So it's a very smart way, if you like, to produce circuits. It's also a very simple process compared to conventional processing. You can simply produce a single or two-layer circuit with a couple of runs through a graphic printer with a particular set of ink and end up with a circuit at the end of it. That can be done in very high volume. You can produce hundreds of meters of circuits very quickly using printing techniques. So the conventional approach for printed electronics is considered to be that we print some circuit and devices onto a substrate, and then we assemble components onto those. Just to give you a summary of the inks and the processes, typically we use silver and carbon and copper inks. Silver and carbon are probably the most common. We also have to have dielectrics that act as insulating layers. And we also make use of complex functional inks for things like sensing of light or temperature or pressure, and also inks that produce light or produce output functions of some other description, heating, for example. So we have a set of different inks that we use to print and create the devices and the circuits that we're looking for. And then we have a number of different techniques. So all the different conventional printing techniques, such as inkjet, which probably we all know, but then other approaches such as flexographic, gravure printing, rotary screen, these are all used to produce printed electronic systems. Serious challenges with this process largely are to do with reproducibility, materials, alignment, registration of components. The print industry is very good at producing high volume of what looks like fantastic pieces of print, but if you're looking in detail, if you're trying to get a 0.1 millimeter registration of components, then you're probably going to struggle with conventional print. So there are some interesting challenges that we'll look at possibly as we go along. I just want to go back to this definition of printable electronics, because it isn't obvious what is meant by printable electronics. Just let the kitchen people finish their tasks. The OEA, the Organic Electronics Association, defines printable electronics as electronics that is thin, lightweight, flexible, robust, and produced at low cost, which is a reasonable definition, but it probably isn't sufficient, because it also requires that we include large area electronics. Many of the devices we create down at CPI are very large area. They can be tens of meters long, half a meter wide. They can contain many, many thousands of components in single assemblies. And these could be single circuits that we're creating. So large area is very important. And then also the use of other forms of structures, not just thin and flexible, but integrating those into other parts to make 3D structures, for example. Printable electronics, printed electronics has grown a lot in the last 20 years, and if you look at definitions, you'll see great long strings of letters such as OLE, TPF OLE, all sorts of combinations of these words. But generally, large area, I think, is a good definition. Organic is mostly there. Lots of these things are organic, although we also print things that are non-organic. And so a good, I think probably a nice alternative summary is just anything you're not doing on a PCB. Non-PCB electronics is really what printed electronics is about. We'll come back to that later, but that might be a new definition. Excuse me. So thin, flexible, formable, that's what it's about. And you'll see various examples as we go through. And there are some nice illustrations here of a range of different types of components, OPVs, batteries, printed sensors, OLEDs, assembled circuits. All of these are fully flexible, can be integrated into very thin structures, and can be formed into 2.5 or 3D parts as well. So what are these form factors then? The key way that we make these things is to form them onto some sort of substrate. The substrates that we most commonly use are things like PET, PEN, polyamide, polyurethane, and even papers. I'm not a chemist, so I put up these the names polyethylene terephthalate and so on just to show that I can use Google. I really don't know anything at all about the structure of the chemistry here. If you do need to know more about that, there are plenty of people around here, or we can help at CPI as well. But the point is that these are very common materials that are used in all sorts of industries, the food industry, packaging industry. These are materials that are produced by the kilometre daily, hundreds of thousands of kilometres daily, in fact, by large companies. And we are using materials that are commonly in use. And that is a benefit in terms of cost, and it is one of the drivers for low cost of printable electronics. Papers are an interesting challenge because, particularly on the recycling front and the sustainability front, paper is seen as a nice alternative and a good substrate material for electronics. And indeed, it is quite possible to print electronic circuits onto paper. There are some interesting challenges that you get with that. The surface morphology can be quite challenging in that if you ever look at a piece of paper under a microscope, you'll see a lot of very rough features on the surface. if you get a surface roughness of 200 microns, you're probably doing quite well with a piece of conventional paper. But it's also easy to treat the surface of the papers to make them conformal, to accept print, to provide a nice flat surface for these things to be reproduced on. And the surface chemistry is also important. It's important that the ink can adhere and stick well to the substrate. So there's quite a bit to consider in just the piece of material that you're producing the circuit on. So we've got a material that we can produce the circuit on. How do we produce it? Well, generally we make use of various forms of inks, and the most common ink I've already mentioned for conductor circuits is silver. So this will be a binder material that contains probably 70–80% of silver solids in some sort of flake form typically, and that is combined with appropriate materials to make an ink that can be printed with the right sort of rheology so that it will work well with, say, screen printing or with flexographic printing. Or if you're trying to do maybe inkjet printing, then you need a very thin, easy to jet material. So the rheology of the inks is a critical part of their assembly. All of these inks come up with relatively high resistivity. If you're electronics designers, you know that we use copper for most printed circuit boards, and the copper that we use is probably what's called half-ounce copper, typically about 18 microns thick of real metal. That's 100% metal pretty much you've got there. And the resistivity of that is much lower than the inks that we use in printed electronics. So you might be looking at tens of milliohm per square compared to 1 to 2 milliohm per square for conventional PCB. And of course with conventional PCB, if you want to, you can make the copper significantly thicker and really reduce your resistance. So is this a problem? Well, generally not, because the resistance that you need for most circuit tracks is actually quite high. It doesn't matter that you've got a few ohms of resistance in a track when you're only passing a few microamps or a milliamp of current through those tracks. These things are not generally terribly important. It does limit the application, so if you're wanting to use your circuits to power large arrays of motors or something like this with tens of amps flowing, you simply wouldn't even consider flexible or printable electronics. So a range of different materials can be used: carbon, copper. There are different forms of copper that are currently being used. We have a process called inkjet flex, which can print a seed layer using a conventional inkjet printer, and then plate a copper circuit on top of that, copper conductor on top of that. That gives a very thin copper layer, but it's a completely digital process, and it means that you can print your circuit onto paper or onto PET, and that's a completely versatile and adaptable sort of way of doing things. There are also organic materials that are used for these inks, so things like PDOT for transparent conductors, again, a relatively high resistivity, but in the right application, that really doesn't matter. So how do we actually create the circuits then? We've talked a lot there about the substrates of the circuit conductors that we're putting together. How do we actually make something active that's going to do it? There are different ways of conceiving this, and the ideal, I guess, would be that you simply put your sheet of paper into a printer. It will print all the conducting layers, it will print the sensing layers, and it will print all of the active circuitry as well. That's probably an ideal that we're not there yet, definitely not. But it is where most people, I think, initially conceive printable electronics to be. Printable electronics, though, is a bit further away than that. We can print circuits by the kilometre, that's no problem. We can print sensor materials by very large areas of them. But the active components, we tend to make use of conventional, off-the-shelf components, so silicon, in fact, and other materials for all of the types of components we use on conventional PCBs. So what you tend to find with a printed electronic circuit is that it is not simply into a printer and produce a sheet of circuits. It's a combination of those technologies with conventional technologies that we assemble the electronic components onto the surface using adhesives, occasionally solder, and we end up with what's termed a hybrid system. So it's a hybrid of flexible, printable elements and conventional components. And you see a couple of different examples there. The image on the right-hand side is a silver circuit, so that's screen-printed silver. The circular dot is a printed temperature sensor. The white layers are insulating dielectric materials to separate the different layers of the circuit. And all of the other features on there are conventional components, in this case plastic packaged, but they could have been bare die components, for example. And then you can go a step further with these planar 2D thin materials and form them into 2.5D or even 3D structures. And so it is possible to create assemblies that can be molded or integrated into other parts. Generally what we're doing is, again, getting rid of the PCB, and we're integrating the electronics into the plastic part. The top right image there shows a molded electronic form from Tech, which is generally a touch display or a touch sensor, which might be being used to activate some controls in a car, for example. It gives some visual feedback there with OLEDs or LEDs that are embedded into the plastic. So all of the electronics here is embedded in the single piece of plastic. Once it's been formed, there's no electronics assembly to do. It's all built in there. Down below that, you've got an image of a strain sensor that's been built into a piece of composite material. So this is this is glass fiber composite with a strain gauge and all the electronics that go with it built into the composite material and wirelessly powered from the phone here. And you can see the little blue LED in the center glowing, and that's powering up the circuit and also doing the strain measurement. And so it means that you can integrate these sort of functionalities and sensing capabilities into, say, an aircraft wing or a structure in an aircraft, to know that you've had several bird hits as you've been going along, and therefore you should probably do something about checking the wing integrity and that type of application. Okay, so that's how we go about making the devices. What do we use to form them? I've said that we often make use of hybrid assemblies of printed circuits, but also conventional off-the-shelf components. However, there are a wide range of printed electronic components around, and selecting either a conventional device or a printed component to build is a critical part of the whole design process. The list here shows all of the types of electronic component that can currently be produced, and you can see that it covers pretty much every electronic component that you would need in an electronic system. The limitation is in the memory and logic area, and we'll come back to that. But sensing, passive components, the large area circuit that you need is your substrate, OLEDs and LEDs, and electroluminescent displays, power, all of these are available in printed forms. And it means that we can produce ultra-thin circuits. So let's look at those in a little bit more detail. The power components. All active circuits need some source of energy. And if we're trying to produce an ultra-thin form factor for a piece of electronics, then it's a bit of a nuisance to have a AA battery tagged onto the back of it. And so there are batteries that are being produced in these ultra-thin formats. There's a number that are shown there. Got a couple. You really can't see these, I appreciate that, but one of the important points about these type of components is that they are incredibly thin. You won't be able to see this. You're welcome to come up and have a look after the presentation. But this is a battery that has about a 30 milliamp hour capacity. I can bend it. It works perfectly well while it's bent, and it will straighten out afterwards as well. It's produced in a very simple printing process. There's no lithography or anything like that that's needed for that. It's conventional printing sort of processes. And these devices really can power electronic systems for substantial amounts of time, even though they sound like rather low energy capacity. If you design your circuit to match, then you've got a good effective system. Supercapacitors are also important. They're a very powerful source of energy for these devices, and they have the advantage over batteries that they can provide much higher current spikes, so they can be good to use in combination with batteries. Energy harvesting is also an important idea. Many of these devices are intended to operate for a very long time. And although these batteries that we can print are not too bad, and we can get devices that might work for 6 months or even a year, if you want devices that will operate for years at a time or require higher amounts of energy, then we have to harvest that energy from somewhere. And so there are a number of energy harvesting technologies around. Photocells are a common approach. Here's a amorphous silicon device, again ultra thin, about 0.5 millimeters thick. I can curl it round and it still works perfectly well. But these can be attached to labels or to other thin devices and provide significant amount of energy, usually accumulated into something like a rechargeable battery or into a capacitor, so that you can use energy whenever you need it. And other sources of energy are available too in printed form. So piezoelectric devices that operate from the vibration of components. You can print a piezo sensor, and if it's operating on a piece of equipment rather that might be buzzing away, vibrating to itself, you can harvest some of that energy to power your electronic sensing system. Thermoelectric generators are also possible to print, although they tend to be a little bit more bulky. I wouldn't say that's a technology that's ready to go quite yet. But RF field harvesting is another very valuable source of energy around us here. All of our mobile phones are buzzing away, Bluetoothing to each other, and Wi-Fi connection into the network here. There's a massive amount of energy, relatively speaking, in the air around us, and we can harvest that energy to power the electronic systems. It's a very nice demonstrator by a company called Williott that shows a Bluetooth device being powered by harvested Bluetooth and Wi-Fi. So it's quite a feasible thing to do. For light emitting devices, there's a number of different forms of component that can be used. Often these are seen to be desirable to have them quite large, and the OLED that you see on the top left of the image here is actually around 10 by 12 centimeters in dimension. And that's a single component that could be used to provide large area lighting. You can see it's flexible, it's built on a plastic substrate. One of the challenges with OLEDs is encapsulation, because any moisture that gets near these materials will cause them to deteriorate very rapidly, in fact. So encapsulation is critical. But other forms of display like LEEC, different electrochemical arrangement, and electrochromic at the bottom is a very useful approach to creating displays on devices that are relatively simple. We wouldn't consider at this stage the idea of creating a high-resolution display with OLED. I know this is being done on your mobile phones all the time, and recently companies, Samsung amongst them, have produced a foldable high-resolution OLED display. But those are state-of-the-art, seriously challenging devices, and the power requirements for that type of thing are very high. The electrochromic display at the bottom here is a non-volatile display. So you apply a voltage to it to change its state. You can then take the voltage away and the display will remain. So those types of displays are great where you've got a limited energy budget and you simply want to note a change of state or a single use of a particular device, for example. The biggest challenge probably in the printed electronics arena, not probably, it really is the biggest challenge, is making active devices, making integrated circuits that are formed in plastic, formable, flexible formats. But there are some very nice technologies that are being used for this, and there is some significant success in producing integrated circuits on flexible substrates. We're going to hear quite a bit more about this afternoon in a presentation from one of the other speakers. So, and I won't go into this in detail here, but there are multiple ways in which we can create flexible transistors on flexible substrates using often quite conventional processing techniques. So these may or may not be printed. It is possible to print an OTFT, or organic thin film transistor, using I've seen this done using inkjet technologies, for example. So it is actually possible to print devices. But if you want to print large numbers of components, tens of thousands, then alternative processing techniques electronics are going to be needed for that. But there are flexible integrated circuits around now, and we'll come back to this, in fact, in the next slide. So the next slide shows this current example of a large-scale integrated circuit that's being produced by a company called Pragmatic. They're manufacturing metal oxides devices on flex. They build their circuits on a 10 micron thick polyamide substrate. They assemble around 10,000 components onto their device, and that chip can perform near-field communication type functionality. So the idea is that this ultra-thin, flexible, and ultimately very cheap component can be integrated into a wide range of products with a single silver print of an antenna, attach the component to it, and you have NFC functionality in your crisp packet, for example. Remarkable technology, and there are other companies doing it. Thin Film have a flexible NFC tag that they've been producing for a while as well, using different technologies. There's been some great demonstrations of even analog components recently, analog transistors, multiplexers I've seen being demonstrated. So it is possible to print these components, but not using the sort of technologies that we would use to print the circuits typically. And then sensors. Sensors are probably one area that most people associate printable electronics with. There's a very good range of passive sensors that can be easily printed. We have printed temperature sensors by the kilometre, quite literally, on our roll-to-roll screen print line at CPI. It is possible to do that. Up in the top right image on the slide here, you see some circular pressure sensors, in fact an arrangement of pressure sensors. That particular application is for up to 128 pressure sensors to be integrated into a crash helmet, so that when you have an accident falling off your bike or your horse, then the medical team can understand exactly what problems you've experienced. Probably the bottom right is probably the most, well, it is the most ubiquitous form of sensor. That's a glucose sensor that's been printed for many years. It is the base load, if you like, for electronic sensor printing, and is produced by the billion each year. So there's a very common use of printed electronics there. But the sensor types can include temperature, pressure, strain, humidity, resistance, and capacitance changes are generally the way in which these parameters are monitored. But even photodetectors, gas sensors, and so on can be printed. Some great demonstrations of those in recent conferences. And biosensors are being developed for a wide range of different forms of biodetection. Glucose is the most obvious one, but there are many other materials that can be detected with appropriate chemistries on the electrodes. And really all you're doing here is printing a carbon, a silver circuit, a carbon and silver circuit, and then sensitizing the top with an appropriate sensing material. So the print process is quite simple. The deposition of the sensing material is also quite simple. These are not complex things to print and produce. And then we've got passive components, because every electronic system requires some sort of resistors, capacitors, and so on to string it together and get the whole system working. These are illustrations of resistors, capacitors, inductors, and antennae, all of which are passives. And we can produce resistances that range from a few ohms to many megohms in small areas. To be honest, it's not that complex, because every resistor you use pretty much in your electronic systems is already printed. It's been printed for a long time. It's part of the assembly process. The capacitors that you see there in the center, little parallel plate capacitors, they can be used to produce hundreds of picofarads or even up to nano or tens of nanofarads if you need them. We can't get up to microfarads, not with conventional capacitors, although a combination of the supercapacitor technologies with conventional printing processes should mean that soon we will be able to get up to microfarads or hundreds of microfarads quite easily on these little printed forms. And inductors are a very straightforward thing to create, although the range is limited in terms of the values that we can manage. The inductor is just a printed coil, usually with a crossover, which is an annoyance, but it is manageable. But we can get tens to hundreds of microhenries rather with inductors, and that means that things like NFC circuits, which require inductances of around 10 to 20 microhenry, are quite feasible to produce using these printing techniques, and that's why we can print NFC circuits and use those a lot in different applications. And then the bottom circuit there shows an RFID antenna. This is one of the most common applications of printed electronics, or these types of technologies anyway. RFID has been around for quite a number of years. All of the tags that go in clothing and more and more even on expensive foods and other drinks and this type of thing. These devices may be UHF RFID, which is the antenna that's illustrated here. The small black square, no, there isn't one on here. So the bottom track there that you see has a narrow gap. That's where the component is added. A bare disilicon component is added onto this copper printed circuit in this case, and that forms an active RFID circuit. But the antenna itself could be of various forms. Okay, so we'll just take a little bit of a pause. What we've been looking at so far is the technology background, if you like, the components and the materials that are available for creating printed electronic systems. And that means that we can understand how we can put these things together, the type of functionality that we can expect to integrate into our systems. And what we'll do on the second half of the presentation is to look at the design and assembly of these components and look at the applications that we can use them for, how we can create smart labels or lighting that's integrated into rigid panels in cars and all sorts of things like this. We'll understand more about how we put these things together and the design and the assembly processes for that. Are there any questions at this point? We'll take a quick pause from me chatting at you for the last half hour. Are there any things people would like to ask? If not, we'll just move on. Yes? Yeah. Yeah, the electrolyte is a challenge, and many of the electrolytes that are used are gels, and so that then creates a different form. If you pop down afterwards, I'll show you a couple of different formats. But the form of the material, the electrolyte can be a paste, essentially, and there are also some solid-state electrolytes that are being developed so that you can avoid the need for a pocket that contains the electrolyte, because that is a challenge. This particular battery doesn't have a gel electrolyte in it, it's in a paste sort of form, which means that it is much more formable. Yeah, it's an interesting challenge. Okay, well let's step on and look at the next stages. So just thinking about the design then of an flexible electronic circuit. It's actually just the same as designing a conventional circuit, really. You go through the normal specification, system design, circuit design, manufacture, product test sort of process. But we stick another bit in the middle there, which is the assembly approach and how we're actually going to put this together. Because with all electronic systems that are conventional, we assume we're going to be making these on a PCB. We might debate whether we're going to do a 4 or 6 layer PCB, but that's about the level of analysis there. In printed electronics, we've got a much broader range of assembly techniques and print techniques and so on. So we've got an extra step that goes in the middle. But other than that, the design process is really just the same. And the design tools that, I'll just skip ahead, the design tools that we use for this are really just the same. Okay, so we make use of conventional PCB design tools to do the layout of printed electronic circuits. We use circuit simulators such as SPICE to help us to understand the performance. That's a bit of a challenge because the components are often new They're only just being characterized. Getting good SPICE models that tell us how an OTFT will operate is quite challenging. And the range of process parameters, the corners, if you like, of your process are really broad when you're printing. It's much less controlled than conventional silicon processing, for example. And so it means your models have to be much more tolerant to parametric shift. But the tools are the same and can be the same tool set that you would use for a conventional PCB design. I jumped ahead, sorry. One of the important characteristics to consider is what should we make into a printable circuit, and what should we say, no, that doesn't really fit printable, let's do that on conventional. These are the key characteristics, really, of circuits that are suitable for printable implementation. Simple functionality, which actually can be quite sophisticated because you can put a lot of complex functionality into a single silicon component, of course. And if you're assembling a bare die or a packaged part onto a flex, the illustration here is got an NFC processor that includes an ARM Cortex-M0 component. It's got a temperature and humidity sensor built onto it as well. So when I say simple functionality, it's not that simple. However, we don't have large arrays we don't have large connectivity available to us. We have 1 or 2 layers or 3 layers of conductors. We don't have 6-layer PCBs or 20-layer PCBs available. So you have to constrain your requirements in that respect. Low power and low current are also both requirements, or desirable anyway. It may be that you have an application where you only want your device to last 10 minutes. We do have one at the moment we're talking about, which is temperature monitoring and a process where a device that's required will only need to last 10 minutes, and then we'll have to be able to read the data out at the end. But it doesn't have a long lifetime requirement. However, low power is often a common requirement for these things. And I mentioned the resistivity of tracks previously, and so low current requirements in the order of tens to hundreds of milliamps is acceptable, but generally lower than that is good too. Simple connectivity, ideally these components are completely wireless, and in fact the majority of them are. They either have wireless power provided to them, they have wireless data, comms in and out, because that is the sensible way to do this. If you have a thin flexible label such as this, you don't then want a USB connector plugged on the end of it to get your data from it. You want to tap your phone on it to extract the data, which is exactly what you can do with this type of thing. And the low component count just makes sense in terms of complexity in the integration. Will challenge things like the reliability of the assembly. Also cost, of course, is going to be a problem. Cost is generally thought to be important. Usually clients will say to us, of course, I always want a cost down, I need this, I assume that your printable electronics is going to be cheap. It isn't necessarily, because the majority of the cost is dominated by the conventional components that you're using. So although it might be cheap to produce hundreds of meters or kilometers of silver printed circuit compared to PCB, if you're paying €1 for a microprocessor, that's not going to change when you do it in printable. So it's an important point to note. Okay, so the design process is pretty much as is for conventional. That's good. How do we put these things together? And particularly, how do we create the electrical connections of components onto substrates? I've not been in printable electronics for a long time, or flexible electronics for a long time. And the idea that, when I first started, the idea of fixing rigid components onto flex substrates and then bending them around sounded like a disaster waiting to happen. Most of my research career was spent in reliability of electronic components. And reliability of electronic systems is largely based on the number of contacts and connections you have in your system. And those are the things that break. So the idea that we might have a flexible substrate connected to a rigid component and get the two bending together really seemed a little bit anachronistic. However, it can be done, and it works extremely well. And by choosing the right connection processes and the right adhesives and so on, we can make extremely reliable assemblies of combinations of rigid and flexible components that have superb electrical performance. And we tend to do that by using conducting adhesives. So solder can be used. Solder is the way that we make PCBs, of course, with conventional components. One of the challenges with the materials that we work on is that these are all relatively low temperature materials. So PET can tolerate up to around 120 degrees centigrade, something like that. If you go much above that for too long, then it will start to wrinkle and deform. PEN can go a bit higher, which is really the only reason we ever use it. And you can process up to about 180, I think, for that. Polyimide is a nice material. That will really allow us to go up to 300 degrees processing if we want to. So for that, we can use conventional solder. But that has a problem of cost. It's a very high cost material compared to PET or PEN. So low temperature processing is an important part of electronics and printable assemblies. And so a number of materials have been identified for this type of approach that use conducting adhesives. And there are two key forms of conducting adhesive, anisotropic and isotropic, and I'll come back to those shortly. There is an area of low temperature solders, and there are solders that will operate down at about 140, 150, probably 160 degrees, so they will operate perfectly well at that. But the other aspect of this is not just the conductors and making the contacts. You have to have a mechanical strength in your assemblies. Because they are flexible, you've got to make sure the components will stay put. And so the non-conducting adhesive bit and films is tremendously important as well. So here's an example of a low temperature assembly that we did. This was an array of LEDs. You can see a copper circuit printed onto a PET substrate. That's about 100 micron PET substrate. The circuit is printed using an inkjet flex process, which gives a very thin copper surface, something like 3 microns of copper. But you can also see that we've got arrays of LEDs there. Those are something like 10 milliamp LEDs, so we've got notable currents flowing through there and quite large arrays. In fact, this whole display was about 5,500 LEDs were powered through this printed circuit. So that was quite a demonstration of what could be achieved in terms of power density and light output and so on. Solder was chosen. It seemed to be the right approach for this particular component. And you also notice that we've got some through-hole components here. We've got an edge connector poking its pins through, which is also soldered onto this particular assembly. And that produced a very nice way of doing a feed out onto a conventional drive circuit. The drive circuit for this is large inductors and quite high power components, so we wouldn't have thought of doing that on the flex. So you've got to think about the sort of partitioning of your system, if you like. What fits well onto the flex technologies, what fits better onto the rigid conventional components, PCBs rather. So you need to think that through. But this was a very successful assembly. As I say, a large area of LEDs, in total like 5,500 on a number of panels, 620 LEDs on this single panel. And we used a solder that is a tin bismuth combination. That's a common way of producing a low temperature solder. It has some silver built into it because that can then help if you're attaching onto a silver circuit. Stops the leaching of the silver out of the inks. However, probably the most common approach that we use for assembly, largely because it's simple, is anisotropic conducting adhesive. And this is isotropic conducting adhesive is simply an epoxy glue with silver built into it. So you add a bunch of silver in, and then you cure your adhesive, and you create a very good conductor. The anisotropic version is somewhat simpler, somewhat more complex in its appearance and how it works, but it works in a very clever way. With isotropic adhesive and with solders, you have to provide a small amount of solder per pin or adhesive per pin. You have to make sure you don't get shorts between them. Anisotropic, you don't have to worry about that. So you can see the example assembly here. We have the grey substrate at the base, we have the blue component on the top, and the bronze-coloured, yellow-coloured bond pads and tracks that we need to make contact between. All that we need to do with anisotropic adhesive is put a single blob of the adhesive over the whole of the component area and then press the component down into the substrate. And that's done at temperature and moderate pressure for around 10, 20 seconds, something like that. What you see happening is that the grey spheres within the pink adhesive epoxy, those are trapped between the conducting pads, and we get conduction vertically between the circuit track and the bond pad. However, the spheres are sufficiently sparse for there not to be any lateral XY sort of conduction. And so with a single blob of adhesive, a single press and heat and pressure for a short time, we can get multiple contacts simultaneously. This is very handy if you've got a component that has a very small pad pitch, for example, 0.4, 0.5 millimeters, and lots of pins together. It makes it a very easy way to assemble these components. And here's an example of an ACA assembly. This is with a smart label that has 24-pin microprocessor on it, 0.5 millimeter pitch. It's got an 8-pin QFN on there as well, which is the little humidity and temperature sensor, and the other small components as well. We use a Dalo anisotropic adhesive for this, and works extremely well. A very effective way of making a very robust assembly. The other advantage of this material is that the pink there is all epoxy, is all cured epoxy. So your whole of your components is mechanically attached as well as electrically attached. And that helps the assembly of the overall device. How do we dispense the adhesives? There's multiple ways of doing that as well. There's always options, it seems, in printable electronics design and assembly. Stencil is a common approach. If you're wanting to use isotropic adhesive, ICA, then a stencil approach is quite feasible, just as you do with solder paste. It's possible to stencil the adhesive down onto your printed circuit, your flexible circuit, place the components, and we'll see an example of this later, and then cure them in an oven en masse, and that works extremely well. It's also possible to use things like syringe dispense, where a small amount of material is dispensed by compressing the syringe over time at a particular pressure. Jetting is used as well. I've got an example here of a Vermees jetting head, which is used to dispense small, precise amounts of material in little jets. And inkjet is also quite possible for dispensing adhesives, although that tends to be challenging because the adhesives often have a rheology that doesn't really match well with inkjet dispensing. And you've got to consider things like the viscosity, the temperature, the drying time. Many of these adhesives are temperature dried rather than thermally dried rather than UV. UV works okay, but if you've got a lot of silver in your adhesive or your ink, then the UV tends to get scattered or reflected back, and so you don't get very good curing. So thermal curing is most common for these materials. And we've already mentioned the idea of the different types of substrates. The common ones that we use, PET, we tend to use 50 to 100 micron PET. 35 microns is about the thinnest we tend to go. You can go thinner than that. 35 microns is a very thin, flexible material. We've used that in things like adhesive patches for medical monitoring, where it's so thin it conforms nicely to the skin. And different types of printing approaches as well. So it's quite straightforward to manufacture small quantities of circuits in this way, using these different materials and circuits and components. But one of the advantages of printed electronics is to get to high volume using mass production techniques. And at CPI, we've recently invested in significant capability to do roll-to-roll assembly and manufacture of circuits, and that's what we're going to have a quick look at here. I'll switch to this next slide. It'll be a bit noisy for a few seconds, but I'll just let it run. So that video shows the assembly of LEDs onto a flex substrate using a conventional PCB machine. Okay, so if you've got Europlacer type equipment that can do PCB assembly, you simply need to mount your flex circuit onto a rigid carrier, and you can do assembly just as you do for PCBs. It's a straightforward process. It's sheet fed, so it's a relatively slow process. We had used conductive adhesives to, we'd screen printed conducting adhesives in that case, but you can also dispense the conducting adhesive through syringe and so on as part of the assembly operation. All the normal things apply, tape fed components. However, this is not really scalable. It's not a high volume manufacturing process. And for that, we really need high-speed roll-to-roll integration, which is what is shown on the next slide. So this next slide shows a roll-to-roll integration process. And you'll see that it looks quite similar to the PCB assembly with one subtle difference. So spot the difference here, okay? Okay, there's the difference, okay? So at the end, the continuous roll of substrate is moved along in a stop-start sort of approach. The pick-and-place machine you see there is a conventional machine from Yamaha called an iPulse, and it can pick and place a wide range of components down to 0201, but also very large components up to even flexible batteries can be picked and placed with this system. The difference is that this is being done on a roll-to-roll continuous process. So we will have several hundred meters of circuit at one end of the machine, which you see down in the bottom left there. You see a cutout of it. I'll show you the equipment in more detail shortly. But it allows for continuous roll production of circuits. This is a diagram showing the different elements of the roll-to-roll multi-component pick-and-place line that we've got at CPI. And it doesn't matter that it's at CPI, the whole point is that it's possible to do continuous assembly of circuits to produce 500 meters of circuit on a roll using this sort of approach. And these are not just single components of RFID components, it's the type of thing that's done all the time around the world. This allows assembly of complete electronic systems with microprocessors, light sensors, LEDs, all sorts of other system components. You can see that it's a continuous roll from left to right. We have an input spooler that takes the 500 meters of circuit. We go through a pre-bonder, which actually can allow direct wafer placement, so pick and place from wafer. So individual die can be placed on the reel as it's going through. We then see the pick and place unit, which is the Yamaha iPulse that I just showed you, followed by a final bond module. That module is applying what are called thermodes. And the thermodes are doing the anisotropic conducting adhesive bonding process. And so something like 64 individual heat elements are pressed down onto components, arranged in the appropriate arrangement, so that you can bond a whole set of components simultaneously as this device goes through. And it's all a stop-start sort of approach. The oven is there for curing of things like isotropic adhesives or even low temperature solder if we wish. And then the final stage is to have a glob top, which is where you can put an epoxy cover over components, maybe a bare die type component. The glob top can provide protection. And then an inspection module at the end does automatic optical inspection, ALI, to make sure that we've got some components where we thought we should have the components. And then finally, the reels are rewound onto a single reel, or they can be split into multiple individual reels. So it's possible to produce hundreds of meters continuously in this way of really quite complex electronics assemblies on a flex substrate. Once you've done that, you need to encapsulate your circuit to protect it and make it usable. A simple piece of componentry, such as this, sorry, this is on the video, but this is a piece of PET that's got copper circuit on it. It's got a couple of components, a bare die. That's not really a lot of use as a functional device. We really need it to be integrated into something like a smart label, or integrated into more rigid components like composites and so on. This slide shows an illustration of one way in which a flex assembly can be integrated into, in this case, a label. And this is called a conversion process. And you can see that what we're aiming to do is create this stack of digital print, some PET, some functional print and components, and then a PSA, which is a pressure-sensitive adhesive to attach all the thing together, and a liner for the backing of your sticky label. Those are all the layers within a sticky label that you might then want to place on your products that you're selling and give some function to your products. The inlays that are produced on the previous piece of equipment, the circuitry and so on, are inserted between conventional graphic print and conventional materials. This piece of equipment that's shown here is called a converter, and it is designed simply really as a big roll-to-roll laminator, but it does appropriate bits of registration and so on. So that's one way of doing the system encapsulation. Also illustrated at the bottom is the example I showed earlier of some circuitry encapsulated within a composite assembly. In this case, the inlay circuit, this is the printed stress sensor going out to the left-hand side, strain gauge, the circuitry in the center. All of that is printed onto a 50 micron substrate. We then laser away any of the material that's not needed so that it's not interfering too much with the composite assembly. But then this can then go into a standard composite assembly process with the appropriate layup and different types of materials. It can withstand reasonable pressures and temperatures to form a perfectly standard piece of composite. And some recent testing we've done with the strength of the materials that result from that show that if you arrange the components carefully enough and in the right way, then you do not necessarily compromise the strength of the composite, which is obviously something that could happen if you put large sheets of material and big lumpy components in there. That could seriously impact the strength of your composite. But if it's done carefully, it's possible to avoid that in some cases. I mentioned cost here. I could probably do a whole presentation on cost, but cost is important to note that actually this isn't necessarily as cheap as you might want. It really is quite a challenge. It is very common to see printable electronics as a low-cost option because it's mass production printing and so on. But as I mentioned earlier, much of the cost at the moment is still dominated by the hybrid components that you put onto the assemblies. And so if you've got a microprocessor that costs €1 when it's put on a PCB, it costs just the same on a flex assembly. And that is what dominates the cost. So rather than look for cost improvements, the benefit of printed electronics is really about form factor, functionality, allowing you to do electronics and put electronics where you really didn't think you could do so. And so that's the thing to look for rather than, I just want this cheap. Okay. The technologies like the pragmatic IC that we showed earlier, that is aimed at low cost and is aimed at less than 0.1 cents per chip. Currently, RFID chips, if you buy them by the million and more, you'll get an RFID chip for 7 cents, 6 cents, 5 cents, depends how many you're buying. That sort of order of cost. Marketing companies are looking to put these sensors and these tags onto packets that cost 0.5 cents each for the whole pack. So they can't possibly think of putting a silicon component on when it costs 10 times that. Therefore, they need devices and technologies like the pragmatic approach and thin film, where the components are less than 1 cent, ideally less than 0.1 cent. And that will come, it's just not quite there yet. It's very close. So cost is an important point to remember and to be realistic about expectations of that. Okay, so we've got 2 more. You've been very good sitting listening for such a long time, but we've got 2 more bits to consider now. Applications of flexible circuits, and then finally a case study of this smart label. So you don't have to think so much for these bits. What can we do with printable electronics? Well, here's an illustration of all of the areas that we know we have had inquiries in on printable. And this also happens to come from the OEA roadmap, the Organic Electronics Association roadmap, which shows all of the areas that companies are interested in using printable electronics in. Ranges from packaging, textiles, white goods even, where white goods you think, well, why would you want a bit of flexible electronics in your washing machine? Well, the idea is this forming idea. So you create the flexible piece of electronics that can then be formed into the front panel, so that instead of having to wire in a piece of electronic circuits behind a piece of plastic, you just fit the piece of plastic and that's got the electronics built into it. Medical and pharmaceutical are very interested in this, largely in the logistics and packaging. Logistics is a very big one. You get a lot of interest in the idea of tagging every product that goes out of a factory, or before that, tagging every part of a product as it's going through production. There are companies, automotive companies, who are tagging, putting an RFID tag into every component on a production line, so that as it goes through the production line, all the origins of all the componentry that ends up with your final product is known. And so you've got a complete track of where your components come from. And for high quality components and quality assurance and this type of thing, very powerful way of doing things. So there are genuinely a lot of applications and spaces in which printable electronics can be applied. Just to take one of those as an example, I'm going to go through applications of smart packaging. And these are different ways in which packaging can be made smart to add functionality in different ways. Package integrity is an important one. Do you know whether your bottle of posh whiskey has been opened before you receive it? Well, with a smart label on it that once it's torn can tell you electronically that it's been torn and not replaced by a fake label, that can be pretty useful. For some reason, they always choose whiskey as an example for this particular application, but I suppose it's very appropriate given where we are. But package integrity, making sure that electronically your package has not been opened previously, is very good. Product integrity is also important, so that you know that it's not gone out of temperature range. This is very common with drugs, for example, making sure that the drugs have not gone over temperature or under temperature in some cases while they're being shipped, and that's the particular example I'm going to show later. Or even things like shock and orientation monitors are very helpful to make sure that the devices, the product has not been damaged or destroyed in any sort of way. Brand protection is another way that smart packaging can be used. You can use the package to verify that the product that you're buying is actually the product it says it is. By tapping your phone, it will link you to a website that says this is the serial number for this particular part. Does it match to one produced by Brand X? Brand X's website says, yes, that's okay, that's a real one. Or it says, no, don't know that one. A very straightforward way of proving brand veracity, really, and also doing real-time verification. It's very effective. Consumer engagement is one we get a lot, where brands wish to allow their users to tap their phone on their bottle of washing up liquid and get some fantastic offer that they didn't know existed. And being electronic, it means that it's completely adaptable and versatile. And I must admit, I find the marketing things a little difficult to understand, and I certainly wouldn't think of them, but they come up with some fantastic ways of using the electronics to enhance their brand performance, which is really very impressive. And another example here of in this case, consumer compliance. Adherence is a massive thing in the pharmaceuticals industry at the moment, making sure that, making sure that users take drugs when they should and don't take the wrong type of drugs and do take all the drugs that they should. Adherence is a tremendously important concept at the moment in the pharmaceuticals industry. And as you see here, it's possible to create a smart pill pack that once you pop a tablet, it's logged by, in this case, it's actually logged by the blister pack and helps to tell the clinician what's being done is as it should be. Most of these concepts rely on RFID, and we'll see a bit more of this in this particular example that I'm going to go through. But the RFID is a very straightforward way for users to interact. It's somewhat more reliable than QR codes, obviously more complex to create and print, but it can provide additional functionality compared to the normal printing approach. So the final stage is to look at the smart label as a case study. And the aim here was to produce a label that could monitor temperature and humidity of pharmaceuticals as they're shipped around, and particularly for clinical trials in this case. Cost was not a concern, which is a really nice thing to hear when you've got a product designed to do, because the drugs that are being shipped can be hundreds of dollars a time. And also it's a proof of concept, really. The aim is to produce some data that's stored on the label itself and can tell the end user what temperature profile, humidity profile, or shock as another possibility the drug has experienced, so you know that it's not gone outside of the temperature range that it's required to operate on. The architecture for what you're trying to create is really quite complex. I mentioned earlier these things have simple functionality. It's simple in some ways, but actually this is quite a complex piece of electronics that we're putting together, and this is all going to be done on a low profile label, less than a millimeter thick in total. So you've got a complete microprocessor system, you've got a battery, you've got sensors, and then you've got power management, and you've also got wireless comms. All of that built into a label. And these are the elements we chose for this particular example. We've done multiple versions of this, in fact, using different processors. The electronics assembly was done using the assembly equipment that I've shown throughout this presentation. We've got quite complex parts, 24-pin QFNs and this type of thing, so not trivial components to try to assemble. And so we used the approach that I mentioned, and this is the label assembly, the final label assembly that we needed. The components there look a little bit non-planar, but believe me, they were in the final assembly. And we've produced many hundreds of these components now, and they've gone through shipping trials, and it is possible to create a printed label, a printed electronics label that has all of this quite complex functionality, allows the user to any point to log and check what temperature the drugs have experienced, know exactly what they've been through, and as a final step, the data can then be uploaded from the phone to, in this case, an IoT platform to illustrate the accessibility of the data, really, I suppose. Also, in this particular case, the project was with GSK, and they had the data transferred directly into their own firewalled data systems. So, in summary, the technologies for flexible electronics are very well established. Flexible electronics and printable electronics have been around for a long time, probably 20 years it's been in discussion. And there are technologies that are flexible and have been printed continually for that time, things like membrane key switches and the drug sensors we saw earlier. So it's a very well-established technology, and the enhancement, the expansion of this into more complex functionality, larger area components, is progressing at a pace, to be honest. And there are many systems now. We have printed tens of meters of LED wallpaper, for example, large volumes of smart labels on very thin form factors. So manufacturing scale-up is in progress. And printable electronics, I think, is a technology that is really here now and can be used with a wide range of applications. And I hope this presentation has given you some idea of the reality of what can be achieved with these technologies. Okay, thanks very much.